to calculate derivatives. People often describe a derivative as finding the gradient function. So here I have a function, f of x, okay? And the gradient function is just change in y over change in x. However, the derivative is a bit more than that. It is the change in y over the change in x as the change in x tends towards 0. Change in y over change in x as delta x tends towards 0. As delta x gets smaller and smaller and smaller, what is the change in the output of the function? Okay? Now, when in calculus, we don't actually write delta y. We use the word difference, d for difference. So when we're calculating the derivative, what we're actually doing is finding the difference in y by the difference in x as the change in x, or difference of x, tends towards 0. Okay? That is what we are doing. We are finding the difference in the output of the function as we change the input by a very, very, very small amount. And this is what the derivative is. And we write it using the notation d by dx of f of x is f prime of x. Okay? So f prime of x is just the derivative of f of x. Now, how do we find the derivative of more complex functions, such as finding the derivative when we add two functions together? Okay? Let the white function be f of x, and let the blue function be g of x. And the red function is the sum of f of x and g of x. And we want to calculate the derivative of f of x plus g of x. How would we do this? So, let's take the same approach. Let me zoom into f of x. We're here, and we take a very slight nudge dx. This causes a change in output of dy. Okay? Now the exact same point, we take a slight nudge in x. And again, we have dy by dx. Okay? Now the red function is just the sum of the heights of the white function and the blue function. Okay? So what's actually happening here is, if I draw the same thing, we're about here. We have the same distance, dx. And because the red function is the sum of the heights of f of x and g of x, the change in height would just be the change in height of the blue function plus the change in height of the white function. This basically means that it is the derivative of the white function and plus the derivative of the blue function. If I put this as dy1 and this as dy2, this is dy1 plus dy2. So, as I said earlier, it is the sum of the change in heights, and the change in height is nothing but the derivative of both of the functions. This means that when calculating the derivative of the sum of two functions, we are just adding the individual derivatives of the two functions. So what that basically means is d by dx of f of x plus g of x is just f prime of x plus g prime of x. Okay? Because as I said, the derivative is the change in y for a small change in x. And you've noted here the change in y is the change in the height, and here as well it is the change in the height. Now if we look at the sum of the two functions, we just have to add the change in the heights for the same difference in x. Okay? And because we're just adding the change in heights, we're just adding the derivatives. So d by dx of f of x plus g of x is the same as the derivative of f of x plus the derivative of g of x. Okay, let's take a quick example. Let's say we're trying to calculate the derivative of x squared plus x cubed. Okay, this is just the same as derivative of that plus derivative of that, which is 2x plus 3x squared. Okay, and this would be true for adding any functions. Okay, even if it's x squared plus sine x. And we could also add more than one function. So x squared plus sine x plus tan x is just the sum of the derivative of this is just the sum of the derivatives of every single function. Now, what if we want to find the derivative when we multiply two functions together? Okay, so we're trying to find d by dx of f of x times g of x. Now, f of x times g of x can be represented as an area. As you can see here, there's this box as width f of x and height g of x. Okay? Again, a derivative is what happens to that output of the function as we change the input by a very small amount. And the output of this function right here is just the area. So if we take a very slight nudge in x, what is the change in area of this rectangle? So let's work this out. Okay? I'm gonna take a very slight nudge. Okay? So I've increased the width. Okay, because I've taken a slight nudge, and the slight nudge is d of x. Now I'm also going to take a slight nudge in x on this side as well. Because remember, it is the change in total area. And if I'm taking a nudge in x, since f of x is a function of x and g of x is also a function of x, the lengths of both sides increase. So it looks something like this. Now we want to calculate the changed area. Okay, the difference in the output of the function for a very small difference in the input. Okay, so what is the change in the area? Let's first see something. We can actually work out what this length right here is equal to, the slight nudge. The slight nudge is the change in length to f of x for a slight nudge in x. This basically means the change in f of x for a small nudge in d of x. And that's nothing but the derivative of f of x. So this width right here is just f prime x. Okay? This is the same for this width right here. It's just g prime x. Because it is the output or the change in the length of g of x for a small nudge in x. Okay? Now I can split this changed area into three parts. We have first this part. Let's calculate the area of that part. We know that the width is f prime of x and the height is g of x. So that part is just f prime x times g of x. Now let's calculate the area of this rectangle right here. It has a height of g prime of x, and a width of f of x. Now, we have also to factor in this rectangle right here. This would be f of x times g of x. F prime x times g prime x. However, remember, a derivative is the change in output as the change in x tends towards 0. So as this reduces, as we reduce the change in x, these rectangles get very, very, very thin. Okay? This means that this piece in the very corner will tend towards 0. The area of that piece will just tend towards 0. So it's negligible. So the area that actually matters is just these two rectangles. And that is just equal to, so the changed area is just f prime x times g of x plus g prime x times f of x. Now this is true for any function. Okay? But let me prove it using a function that you can easily calculate the derivative of. Let f of x equal x squared and g of x equal x cubed. Okay? When we multiply these two functions together, we get x to the power of 5. And the derivative of x to the power of 5 is just 5x to the 4. Let's prove that using this idea. Okay? So instead of f of x up here, let me just erase that. We have x squared. Instead of g of x over here, we have x cubed. Okay? Now, for a small nudge in x, what is the change of x squared? That is just the derivative. And we know that comes down to 2x. Okay? And obviously this length right here is still going to be x cubed. So that area is just 2x times x cubed. What about here? What is the change in x cubed for a small change in x? Is just the derivative of x cubed, which is 3x squared. So the height is 3x squared, and the width is x squared. So this area is 3x squared times x squared. And as mentioned earlier, since the change in x just tends towards 0, this corner piece is negligible. Now, we just have to add up these two areas. And we get 2x times x to the 3 plus 3x squared times x squared. 2x times x to the 3 is 2x to the 4 plus 3x squared times x squared is just 3x to the 4. And this is the same as 5x to the 4. Which is the same as what we calculated earlier. So this method does work. And it works for absolutely any function. As mentioned earlier. We calculate the derivative of a function inside of another function. For this approach, let's first start off with our labeled functions. Let g of x equal x squared and let f of x equal x cubed. And we want to calculate the derivative of g of f of x. And we know that this is equal to x to the power of 3 all raised to the power of 2. And this is the same as x to the power of 6. And we know that the derivative of this is 6x to the 5. But how do we get this for more complicated functions? Or even unknown functions? Now, I have 3 number lines here. When I take a slight nudge in x, what happens? I just shift this by dx. Okay, there's a small difference in x. Okay? Now, this difference in x happens over here too. So in this number line, which has mapped x cubed, there is also a slight nudge in x has been caused. Okay? Now, what is the change in the value of x cubed on this number line? This represents the derivative of x cubed. What is the change of x cubed for a slight nudge in d of x? And this is just the derivative of x cubed, just 3x squared. Remember, I've taken a slight nudge in dx, and now I'm seeing how has the slight nudge of dx changed the output of x cubed. So write this on the side, dy by dx of x cubed equals to 3x squared. So the change in y is 3x squared times dx. So the change in the output is just 3x squared times dx. Okay? Now, here we have a number line which maps a squared. What happens to the output of this function, or what happens to the change on the length of the number line when we shift a by a very small amount? It's the same idea. what is the change in a squared for a small change in a? It is just the derivative of a squared, which is 2a dA. Because dy by dx of a squared is 2a. So dy, the change in y, the change in the output of a squared is 2a times dx. Okay, sorry, in this case it's dA, because a is the input, the difference in a. Okay? Now, notice that the value of a here is just x to the power of 3 in order to get this function. So a is equal to x to the power of 3. So, when I'm saying, so that means, so we now have calculated that the derivative of this function is 2a times dA. Okay? And dA is just the change in the value of x to the power of 3. But we've already calculated this. It's this value right here. So the difference of a caused by a slight nudge in x is 3x squared times dx. And this value is equal to the difference of a. So we're actually just doing 2a times 3x squared dx. Because 3x squared dx is the difference of a. Now, we can substitute x cubed into this value of a. So you get 2x cubed times 3x squared dx is the change in y of this function. And if we multiply everything together, we get 6x to the 5. Dx is dy. So dy by dx is 6x to the 5. And that matches what we got originally here. So for a quick recap, I am first seeing what happens to the inside function for a small nudge in x. So what is the change in output of the inside function for a small nudge in x? And we have worked that out to be 3x squared times dx. Dx being the slight nudge. Okay? Now the outside function is this squared. So what happens for a slight nudge in a? Is we get 2a times dA. That is a change in a squared for a slight nudge in a. Now, a is actually the value of x squared. X cubed. So when I'm saying a slight nudge in a, that is actually the slight nudge of x cubed for a small nudge in dx. So what is the change in the input of the function? And the change in the input is the change of x cubed, because a is the input and a is equal to x cubed. And this change is 3x squared dx. So I've substituted that into dA. So we have 2a times 3x squared times dx. And 2a is just 2 times x cubed. And I multiplied that out and got dy by dx. Now this idea will work for any function. Any two functions, sorry. And what it really is it's just the two derivatives times each other. The general notation for this is d by dx of g f of x is f prime x times g prime f of x. Thank you very much for watching.